so that I don't cut into Haipeng's time. So we've got off to a really good start with Shipra's talk. And in some sense, Shipra's talk gives you a good sense of what we want to cover as part of this program. So in some sense, what we thought when we came up with this program is that we want to think about Bayesian and minimax approaches to sequential decision-making problems. And many of you may sort of think, like many of us work on this and we think that this is a really sort of hot and ongoing area, although the title that I just said, or the small description I gave, Bayesian and minimax approaches to sequential decision problems, if you search for it, you'll realize that this was actually a title of a paper written all the way back in 1949 by Ken Arrow, David Backwell, and Abraham Gershik. So even though the problems feel really new, they've been around for a long time and many different communities have been thinking about it. And we have many of you here today and during the semester to sort of discuss with each other as to how we think about these problems. So I'm Sid Banerjee. I'm one of the co-organizers of this program. We have the three other co-organizers. So Shipra Agarwal, who you saw earlier today, is one of the other co-organizers, as well as Thodoris Likouris and Shuchi Chawla. And in addition to us co-organizers, we have 4 workshops, so the boot camp, and then 3 other workshops, each of which have a team of people helping organize this. And especially for the boot camp, this is being organized by me, Nika Haktalab at the back, and Adam Wehrman, who is online somewhere and who will be here from tomorrow. So we would love feedback on this. We would sort of, please feel free to catch up with us and tell us about what we're doing and what else we could do to help out. And now, in addition to all the organizers, we also have an amazing team of research fellows. So we have 7 research fellows who will hopefully introduce themselves over the next few days as part of being the sort of session chairs. And as part of their duties, what they're doing in addition to the talks is they'll be preparing some kind of like a side document, a blog post of some sort to go into more details into each of these talks. So keep an eye out for that. And if you're interested in following up on these topics, we should have some material available so that you can sort of read that up before you come for the next few workshops. Okay, so that's all I wanted to say about the program. So the next talk is going to be given by Haipeng, and Haipeng's going to sort of switch tracks. Instead of thinking about the stochastic version of the multi-arm bandit, he's going to look at the adversarial version. And briefly, so Haipeng is assistant professor at USC. And before this, he was at Princeton and also Microsoft Research. And he is one of the foremost experts in this area. And one way to sort of see that is many people consider there are 3 main sort of conferences for learning. So ICML, NeurIPS, and COLT. Haipeng, I believe, has won a best paper in all 3, which I think I propose we henceforth declare the Haipeng Slam. So over to Haipeng.
Thank you. Thanks for having me. So yes, I will be talking about adversarial version of multi-arm bandits, and which is, I guess, arguably less known compared to stochastic bandits. But I promise it's going to be interesting and helpful, okay, useful. So so given Shipra's talk this morning, I don't think I need to motivate this problem anymore. So let's just directly go into the formal formulation, which is first a study by our Cesar Bianchi, Front, and Shapiri 2 decades ago. Okay, so here's the formulation. Again, so you learn for T rounds, and as the learner, each time you pick one of the K arms. Okay, so Shipra was using N as the number of arms this morning, so I will switch to K. And so IT is the arm that you select at time T. Okay. So now the important change is that there's an adversary that simultaneously decides a loss vector LT. Okay, so that so LT is a vector, k-dimensional vector, so that each coordinate LTI denotes the loss for arm I. Okay, and I assume that they are normalized, so that every loss is between 0 and 1. Okay. So again, I'm switching from rewards in the morning to loss. Okay, which is for some reason is the convention for this topic, and I will come back to this later. But obviously you can translate between rewards and losses. Okay. And the important thing here is that the adversary can decide the loss vector in some arbitrary way. Okay. It doesn't have to be drawn from some distribution. Okay. It can depend on the algorithm, can depend on the learner's previous behavior, and also can even depend on the distribution for this round of IT. Okay. It cannot depend on IT because otherwise it's just too difficult for the learner. Okay, otherwise it can depend on all the things in the past. Okay, so that's the key difference compared to stochastic MAB. And finally, as always, the learner suffers and observes only the loss of the arm that is selected. Okay. So that's the formulation, and as the goal of the learner is still to minimize regret, which is very similar to the stochastic case. So the regret is comparing the difference between your total loss and the loss of the best fixed arm. Okay. So I star, I will use I star to denote the overall best arm in hindsight. So and you want to compete with this best arm. So if your regret is sublinear, again, it means that on average, you are doing almost as well as the best arm. So stochastic MAB that we discussed this morning is obviously a special case of this formulation where these loss vectors are generated in some IID way. Is that clear? Right? So now let's take a closer look. So first, why do we care about adversarial losses? So when do we have adversarial environments? Well, I mean, so maybe we don't always have an adversarial environment, but I think the key point is that here we want to remove any distributional assumptions. Okay, there's no assumption at all on the loss vectors, which hopefully leads to more robust algorithm. Okay, and also, the second reason is that for some cases, for example, if we are playing games using these kind of multi-bandit algorithm, then indeed you are against potentially adversarial opponents, in which case this kind of adversarial setting is very helpful. And second question is why do we care about regret? Okay, in particular, why do we care about this formula? So there are two very natural questions. The first is, why do we compare with the fixed arm, I star, while the losses are changing? Right? So in the stochastic case, it makes sense. There's one fixed arm, the fixed arm, okay, the best arm. Okay, but in the adversarial setting, the losses are changing. So why do we still care about the best arm? So maybe there's no single arm that's good overall. So why do we still care about this? Well, so this is a valid concern, and there are many fixes. So all these different notion of regret or stronger notion of regret, they propose to kind of address this kind of issue. Okay, so that's a valid concern, but there are other fixes that we are not going to talk about in this talk. And the second question is, why do we still compare with the same LT sequence while the behavior has changed? So we're asking ourselves, in retrospect, what happened if I keep picking I star? What I would have suffered. Okay, but in this case, if you are against an adaptive adversary, maybe LT has also changed, right? So that's also a valid concern. But so first of all, notice that this notion at least makes sense for something called a previous adversary. So for adversary that design LT independent of your past selected arms. Okay, so the adversary can still look at your algorithm and still can design LT in some arbitrary way, but just not dependent on your past actions. Okay, so in this case, then LT is fixed no matter what I pick. Then this regret makes total sense. Okay. But even if you're against an adaptive adversary, so an adversary that can depend on your past action, there are fixes. So one notion is called policy regret. That's exactly to kind of address this concern. Okay. But I want to emphasize that even despite all these issues, studying the standard regret in the adversarial setting is still very meaningful. Okay, for two reasons. First, is just a foundation of all these other stronger regret measures. Okay, in the sense that you either extend the techniques for minimizing the standard regret to these stronger notion, or in some cases you can even reduce this problem to minimizing the standard regret. Okay, so that's why standard regret is fundamental despite all these issues, and that's why we care about this. And also for games, when you in fact you are playing against an adaptive adversary, it's still somehow this standard regret is still very meaningful, right? For example, sublinear regret actually implies convergence to things like equilibrium or optimal social welfare. Yes, even though it seems like this doesn't make sense in the adaptive case, but still it has strong implications. So that's why we care about regret, and that's why in the rest of the talk we will focus on how to minimize this thing. I hope this convinced you. So feel free to interrupt if you have any questions. Right? So to me, I see this problem or other extension as a marriage between two literatures. One is the online learning with adversarial losses literature, and the other is just a bandit feedback, or more generally, any partial information feedback setting. Okay, and it again, to me, it even has a deeper root in the first literature, so online learning with adversarial losses. And I say that because as far as I know, all algorithms for these kind of problems are based on the following recipe. Okay, so first you come up with an algorithm that works with full information feedback. Okay, so in multi-bandit, full information just means that LT, the entire loss vector, is revealed at the end of round T. Okay, so you not only see the loss of the selected arm, but also loss for all the other arms. Okay, so that's kind of like the typical problem in the first kind of literature. So you first do that. And then in the bandit setting, what you need to do is just to come up with the loss estimator. Okay, you don't have the full information of LT, but you just, based on what you have, to construct the loss estimator, and then you just feed it to the full information algorithm. Okay, so that's usually the recipe for these kind of adversarial bandit problems. And the key challenge is really, you need to do these two in a way so that the variance of the estimator is well controlled. Okay, so that's the most important thing that we will keep discussing today. Okay, and because of this, for this talk, I will start with the full information case as a warm-up. Okay, we discuss how to design an algorithm even for the case with full information. Then we will go to the bandit case, and I will highlight how to control the variance of the estimators. And I will also highlight the differences between these two settings, like with full information or with a bandit feedback. Okay. So now let's directly go to the full information case, which is also known as the expert problem. So again, it's just the full info counterpart of adversarial MAB, and it's first proposed by Fron and Shapiri. So it's exactly the same setting. You pick an arm. The adversary can decide the loss vector arbitrarily. You suffer the loss of the selected arm, except the only change is that you observe the entire loss vector instead of just one coordinate. Okay. Same goal, you want to minimize regret, exact same goal. But if you think about it, this is not trivial, even with full information, right? Because again, the losses are changing over time. So how should I know which IT to select? Okay. Yes.
What does the adversary knows all the history of the term T? What does the adversary know?
Yes. Yeah. Good question. What knowledge does the adversary have? Yes. The adversary knows the algorithm, but not the randomness, and also everything before time T. Right, so you probably have seen this problem and its classical algorithm, which is something like this. I will just directly show the algorithm. So it's easy to see that you have to randomize. I'm not going to go into it, but it's necessary. And you're going to sample IT from a distribution PT such that PTI is proportional to this thing. Okay? So the weight to pick I is proportional to e to the minus eta for some learning rate, positive learning rate, times the cumulative loss of mi up to time t. So it's very reasonable. Like if the cumulative past cumulative loss is large, you're going to pick this mi with smaller probability. Okay. And this is again one of the most classical algorithms, called by many names. Is discovered but in many different areas independently. Here I will just call it hedge. Okay. And then okay, this is also not the only algorithm. There are many other algorithms, but this is the most basic one. Right. So that's the algorithm. So now let me just give you a very simple analysis, just one page. So we're going to do this potential-based analysis. So I'm going to define the potential phi t in this way. Okay. So it looks complicated, but notice that this summation is nothing but the normalization factor in the definition of pt plus 1. Okay, so pt plus 1 is proportional to something like this. When you normalize, this is exactly the normalization factor. Okay, so that's the potential. So as always, we study the kind of the increase of the potential between two consecutive rounds. Okay, and so this is by definition just this, okay? Nothing special. So now let me split the numerator into two terms. Okay, the thing that depends on the past before time t, and the thing for time t. Okay, again, equality. So now if you look at this orange part, it's exactly PTI. Okay, so again, by definition, the algorithm said that PTI should be proportional to this, and by proportional, it just means it's exactly this. Right? This is the normalization factor. Okay, so in other words, the increase of potential is just simply this. Okay, so now the rest is just kind of some calculation. Your first thing to do is to approximate this exponential by a quadratic. Okay, let's use something like this, which is true whenever z is positive. Okay, and it translates to a condition that LTI has to be positive. And again, I assume LTI is between 0 and 1 in this case. So we can just approximate this exponential by this quadratic. So let's simplify it a little bit. So sum over I of PTI is 1. The second term becomes this inner product. And the final term is this quadratic term. Okay. So last inequality just by bounding a log of 1 plus z by z, okay, which is always true. So then you get this. Okay, so the eta cancel here and eta squared cancel with 1 eta, you get 1 eta. Okay, I hope that's clear. So now obviously you just sum over t and telescope and rearranging, then you get something like this. The loss of so this is exactly the expected loss of the algorithm, right? You pick ID according to PT. So PT dot LT is exactly your expected loss. It's bounded by the increase of or the decrease of the potential plus this quadratic term. Okay. So the final step is just to realize that by definition, this final potential is actually related to the loss of the best arm. Okay. So by definition, it's something like this. So notice that there's a sum of k positive terms here. Let's just lower bound it by the terms that are related to I star. Okay. I'm bounding this k terms by just one of them. And then log and exponential cancel, 1 over eta and eta cancels, you just get this, which is again the loss of the best arm. Okay. So so again, it means that this term is basically the loss of the best arm. You move it to the left, you get exactly the regret, right? This is just a regret. So I'm using this as the basic vector with the I stars its coordinate being 1. Okay, your expected regret bounded by the initial potential plus this quadratic term. right? And by definition, the initial potential, when there's nothing here, you just get K, right? So you get log K over eta plus this thing. Okay, so let's recap. At this point, so I have proved this expected regret bound, and the only condition I've used here is that LTI is positive or non-negative. Okay, it can be as large as you want, but this bound holds. Okay, and this is going to be important for the bandit case. Okay, just keep in mind. Okay, but for the full information case, when these LTI, they're all bounded by 1. So obviously, this term, this summation over I is just bounded by 1. So sum over t, you get eta t. So you have log k over eta plus eta t. And when you pick the optimal eta, you get root t log k. Okay, so that's how you prove a regret bound for the Hedge algorithm. And this turns out to be information theoretically optimal. Okay, you cannot do any better than this. Yes.
So if you have a condition that loss is between 0 and 1, so if
Yes.
you put modeling rewards and you have negative loss, they're easy fix.
Yes, you need to shift them to positive losses. Okay. So for full information case, it doesn't matter. You can just do negative losses. But the important thing is for the bandit case, which I will
Just
discuss.
using the fact that L is to use the exponential inequality.
Yes, but in fact, so if LTI, let's say, is larger than -1, then something like it also holds, right? Maybe a larger constant, maybe. But it cannot be too negative, and that's the case in Bandit. So clear to everyone? Okay. So before we move on, let me just give you a kind of a more modern view of this kind of algorithms. So at this point, it's kind of well known that Hedge is actually a special case of a more general framework called follow the regularized leader, FTRL. Okay, so this kind of general algorithm, it looks like this. So again, your distribution at time t you're trying to minimize the sum of these two terms. Okay, so the first term is just in terms of the previous cumulative loss. Okay, that's very intuitive. You want to find a p to minimize the loss that you have observed so far, but you also want to regularize this. Okay, so psi here is a regularizer of p. Okay, and this, again, eta is some learning rate. Okay. So the algorithm is more stable than just following the current best expert. Okay. And again, Hedge is a special case in the sense that when you pick psi of p as the negative Shannon entropy, which is this, then you can verify that this is exactly the same thing as the Hedge algorithm that I showed you earlier. Okay. And so we will be seeing more other kind of regularizers in this talk, and we will be also using this regret bounds. Okay, so this is a bounds that holds for general regularizer. Okay, it holds under some condition that will be satisfied for this talk. I'm not going to go into the details, but let's look at the bound. Okay, so again, it's saying that for any distribution you want to compute to, right? Your regret, again, p star is bounded by the sum of these two terms. Okay, so the first term is usually called the kind of the regularization penalty term, which I will always use a blue to denote. So if you see this is psi of p star, again, p star is your competitor minus the minimal value of psi. Okay, so usually you have no information about p star and you just bound this by the maximal value of psi. So that the penalty is actually exactly just the range of the regularizer. Okay, that's the penalty term. And the stability term, which I will use red to denote throughout the talk, is something like this. So here, this notation, it means this kind of quadratic norm. This kind of local norm, I call it. Okay, so it's LT transpose times the inverse Hessian of your regularizer evaluated at PT and then LT. Okay, it's just a quadratic norm with respect to a matrix, and the matrix is the Hessian inverse at PT. Okay, so it's called stability term because it's indeed a bound on like how close PT and PT plus 1 are. So how stable your algorithm is. If this term is small, it means the algorithm is stable. It's more stable.
I'm sorry, can you explain again why the second term represents stability?
Okay, so actually I didn't prove it, but intuitively, you see the difference between PT and PT plus 1 is just LT here. That's the only difference in when you look at the definition of PT and PT plus 1. So when LT, intuitively, if LT is large, you're less stable. Yes.
The reason, I mean, is there a particular reason you're using a time invariant regularizer, or this would still work?
Yes, a good question. So this is the most basic form where you use the same regularizer in every time, but indeed you can do something like time varying regularization. Yeah, but for this stuff, I will just do the simplest case. All right, and so again, I'm not going to prove this bound, but we are going to apply this bound multiple times in this talk. And let's just again verify back to the Shannon entropy case where this algorithm is just hedged. So you see that the range of Shannon entropy is of course just log k. Okay, that's the log k over A that we had before. And then this stability term. So okay, let's first look at the Hessian. So the entropy, the derivative is just 1 plus log p. The second derivative is 1 over p. Take the inverse, you get p. Okay, that's how you get the p. And this is of course a diagonal matrix. So that's why you get this. Okay. And this is exactly the same bound that I got in the last slide. Yeah.
How should I think about the trade-off between the penalty term and the stability?
Yes.
Like if you increase the coefficient next to the stability, like sort of make it put a stronger function over there. How does the behavior of the algorithm change?
Yeah, it's a very good question. So basically, like, I mean, intuitively, if you make this larger, then this has to be smaller, right? If you make this larger, then the algorithm is more stable. And we are actually going to see different trade-offs later. But I mean, overall, you see that this is independent of t, but this is going as t. So the kind of the right trade-off is always separated to be something like 1 over t. All right. So that's enough for the warm-up. And so now let's go into the Bandit case from full information Bandit. So the obvious issue in MAB when you try to apply this algorithm is, of course, that you don't see the entire loss vector. And as I said, the standard solution is just to construct a loss estimator based on the information that you have. Okay, and standard one is just the kind of the inverse importance weighted estimator that I assume you have seen in many different contexts. Okay, so let's define this loss estimator LT hat in this way. So the ith coordinate is just the loss of mi divided by the probability of selecting mi times whether you indeed select this arm. Okay, recall it is the actual arm that you select for time t. Okay, so first of all, notice that this is non-zero only for one coordinate. So for the I, that's the selected arm. For all the other arms, it's just simply 0. Okay, so that's why it's actually computable using just the information you have. You only see one coordinate, and only for that coordinate, you will have the loss divided by the probability. And all the other coordinates, you just set it to be 0. That's why it's computable. And second, second clear fact is that it's unbiased. So in the sense that when you take expectation with respect to this IT, you get exactly the loss of I. Okay, and this is easy to see because the expectation of this indicator is simply just the probability of picking this arm. And obviously it cancels with the denominator. So you get in expectation, L hat is just L. Okay, so that's why this estimator makes sense. And as I said, once you have an estimator, all you need to do is just to feed this estimator to the full info algorithm, as if this is a full info problem. Okay, and that's if you do this, you feed this to hatch, you get the classical algorithm XP3. Okay, it stands for exponential weight for exploration and exploitation. And again, this is the update rule of the algorithm, and instead of using L here, you use L hat. Okay. So now let's pause and think about this algorithm a little bit. So where exactly is the exploration? Okay, so we know from this morning that for these problems, we have to exploit and explore. Okay, so in UCB, you have this exploration bonus term to help you explore. But for this algorithm, where exactly is the exploration? Okay, so the answer is that the exploration is implicit in the sense that just look at what happens every time after you pick an arm. Okay, after you pick an arm, the loss for every other arms is 0 by definition, but for this arm it's not it's at least 0. Okay, and most of the time it's just positive. Okay, and based on the update rule, of course, next time the probability of picking the same arm will be smaller. Again, whenever you pick this arm, next time you will pick this arm with smaller probability, and that's exploration, right? I picked it this time. Next time I will explore other arms. So that's why it has exploration and it's kind of implicit. And this also finally go back to this question. There's indeed some asymmetric between losses and rewards. Okay, so when you're dealing with rewards, you cannot just simply just negate it and do negative losses. Okay, that's not going to work for the same reason. Like if there's no negative side here, this is positive. It means that every time you pick this arm, the next time you will pick it with even higher probability. So then there's no exploration. So obviously this algorithm is not going to work. Okay. Yes.
It's not so obvious, right? Because it's still normalized. So if it's all low reward,
no, it is because again, every other arm gets 0, and you get something non-zero. You get something positive. So next time you have to have a larger probability. Okay. So that's why you cannot directly just do negative losses for rewards. And so of course you can still do with rewards, just shift it to positive. Okay, let's say the rewards of between 0 and 1, first take negative and then +1. So that everything is positive. Then you can use this always. Right, I hope that's clear. And so now let's look at the regret of this classical algorithm. So as I hinted before, the key challenge is really the variance of this estimator. Okay, so if you look at, again, this estimator, and okay, by variance, I always mean second moment, okay, expectation of the square. So again, the expectation is with respect to IT. So by definition, it's just this. So squaring the indicator, of course, gives you the same thing. And expectation of the indicator is PTI. That's why in the end, you get 1 PTI in the denominator. Okay. And this can be huge, right? If you pick I with very small probability, then you have a large variance, which makes sense because with very small probability, you will get information about this arm. Okay. And there's really no way to avoid this. You cannot come up with an estimator so that every arm has a constant variance. That's impossible by only looking at one entry of this loss vector. Okay. And record that the loss vector is changing over time. So that's all the information you have. The information from the past, it doesn't help. Okay. And again, there's no way to avoid this. But what you can control is how the variance affects the regret. So what you are going to pay. So how is your regret going to depend on the variance? Okay. And now, let's come back to this bound that we proved earlier. Okay. So I emphasized earlier that this bound only depends on the fact that LTI, they are positive. Okay. And no matter how large these losses are, this bound still holds. Okay. And that's indeed the case here in the Bandit case when I'm doing this estimator. So they're positive, but they can be very large if PTI is small. Okay. But this bound still holds. So again, you have the penalty term here and stability term here. So now let's see why it's important to have this kind of thing. So you see that when you take expectation on both sides, on the left you basically get the expected regret, and at the left you get expected regret, and on the right you have this, and you see that. So again, this expectation of the L hat square is just this variance or second moment. Okay. And it's actually controlled by this actual PTI. So you don't simply just pay for the variance, but instead you pay it like a PTI fraction of it. Okay, and just plug in this calculation, you see that there's some magical variance cancellation happening here. So this PTI cancel with this PTI. Okay. That's why even you can have large variance, it doesn't matter. So in the end, this term, of course, sum of I, it becomes K, sum of T, you get TK. Okay. So now your stability term becomes eta TK. And of course, when you pick the optimal eta, you get root TK log K.
And so this is really dependent on the fact that like that's the Hessian of
exactly. This kind of local number really is the key to for all these kind of algorithms. And we're going to see more examples later as well.
To pay an extra square root K.
Extra square root K? What do you mean?
You just pay an extra square root K for cancelling the P.
Yes, that's exactly right. Yes. So again, if we've mentioned this term is just 1, now it becomes K. Any further questions? So there's one caveat here that I kind of mentioned. So when I say the left-hand side in expectation is the expected regret, I actually cheated a little bit because this only holds when the adversary is oblivious. So when I star, the best arm doesn't depend on the learner's behavior. Then when I take expectation, I indeed get regret. But if I star actually depends on everything in the adaptive adversary case, then I cannot like take expectation easily, and I have to do something else. Okay, so I'm not going to discuss that, but basically you have to first prove a high probability bound, and then you take then you get the expected bound. Okay, and that requires changing the algorithm a little bit. But eventually you can still get something like this. Right? If there's no further question, so let's look at the lower bound. Okay, we have an upper bound now, and the lower bound is of course root TK that you already saw from Shipra's talk this morning. So Shipra's lower bound is for a stochastic case, and a lower bound for stochastic case is of course also a lower bound for the adversarial case, because adversarial is only harder. Okay. But let me just give you a kind of informal proof, a very quick informal proof. It's not difficult at all. So first, imagine an environment where every loss is just simply Bernoulli 1/2. Okay, every arm is the same across all the rounds. So now give me any algorithm. Let me run this algorithm in this naive environment, and then there must be an arm that is not selected more than T/K times. Let's say in expectation. Okay, that's always exists such an arm. So now what the adversary can do is just to kind of secretly change the loss of arm J to something slightly better. So this arm that the algorithm not selected often enough, let's make it the best arm, just by a little bit, by a fact a gap of root k over t. Okay. Now in this new environment, let's run the same algorithm again. The claim is that the algorithm wouldn't realize the change information theoretically, right? Because you're trying to distinguish these two Bernoulli. And then, right, information theory tells you that you need at least 1 over gap square, and this is a gap. So you need kind of like, say again.
Plus or minus?
It's minus because I'm doing losses. Okay? So then this becomes the best arm. Okay. So you need 1 over gap square, which is t over k. So you need this many times to distinguish these two Bernoulli. But as I said, this j is selected, so that's not enough, right? And so formally you can prove that the same algorithm will not pick j often enough. For example, it will pick it less than half of the times. Okay, and then basically you have the bound. Every time you're not selecting arm j, the best arm, you incur the gap amount of regret, and you're not picking it for half of the times. That's why you suffer root tk regret. And that's it. You can make every step formal, but this is kind of the idea. Okay. So now, obviously, the natural question is that there's a gap between the lower bound and the XP3 upper bound, a gap of root log k. So which one is tight? So it turns out that the lower bound is tight, so meaning that you can improve the algorithm. And here's the algorithm. Okay, so we're gonna use FTRL again. So in fact, in this entire talk, we will just be using FTRL, but just with a different regularizer. Okay, so recall that this is just the common form of FTRL, and you just need to decide the regularizer. For XP3, we are doing Shannon entropy. And now let's do a different regularizer. Let's do Saris entropy with an exponent of 1/2. So Saris entropy is a family of entropies, and basically depending on the exponent of pi, you get different form of Saris entropy. And now let's just do 1/2. So you get root pi. So this algorithm is taken, this simplified form is taken from Abernathy, Lee, and Tawari, but it's really based on an earlier, more complicated algorithm by Audibert and Buback. Exactly. You have so Saris entropy in the limit when this exponent is 1, then you get Shannon entropy. Okay. So let's do this, and then let's now analyze the regret. So record, I show you this general bound, and we are now just going to apply it. Okay. So obviously you need to just figure out these two terms, the penalty term and the stability term. So the penalty term, like I said, is roughly just the range of the regularizer. And in this case, the range is just root k. It's very easy to see. The maximum is achieved by a distribution that put all the weight on one arm, and the minimum is achieved by uniform. Okay, and that's where you get root k. And now let's look at the more interesting part, the stability term. Okay, again, definition is this. And let's look at the Hessian. Hessian is, of course, again, a diagonal matrix because it's decomposable. So the derivative is 1 over root. And then the second derivative is 1 over p to the 3/2. And you take the inverse, you get this. So notice that for Shannon entropy, you have an exponent of 1 here. And now you get 1.5, which is smaller. So you have a smaller stability term. Okay. And now the next step is, of course, just take the expectation so that this is a variance. And as we did before, variance is roughly 1 over PTI. So it's cancel with exponent, you get root PTI LTI squared. And of course, by bounding this by 1 and then close this wall, you get this is bounded by root k. Okay. So now the important thing is to notice is that now I'm achieving a different trade-off between the penalty and the stability term. For Shannon entropy, I'm getting log k for penalty and k for stability. And for Salas entropy, I'm getting root k for both. And of course, in the end, my regret is actually the product of them. Okay, and this is Salas entropy is exactly log k factor better than the Shannon entropy. Okay, that's exactly the last step. You regress this by picking the optimal eta, you get root tk. And it matches the lower bound exactly without any logarithmic factors. Okay. So you don't have to do 1/2. You can do something like 1/3 or 2/3. It doesn't matter. If you do 1/3, you get maybe a k to the 2/3 here and k to the 1/3 as a stability term. Just a different kind of trade-off, but in the end, the product is the same. Yes.
With the general function psi is different, I believe, from the basic proof we saw. And does it also require L hat to be non-negative?
Yes,
Okay.
it does. All right. So that's basically it. That we have the minimax regret for this problem already. So you might wonder, like, so okay, we remove the log k. Why does it matter? It's just a small term. So first of all, for me, given the fundamental, how fundamental this problem is, I think it's important. But it turns out that more importantly, this result turns out to be very fruitful, or this algorithm. And this is kind of a teaser for Sadori's talk in an hour. So it turns out that this algorithm is not only minimax optimal in the adversarial case, which we just proved, but surprisingly, also instance optimal for the stochastic case. So in the stochastic case, if you run the algorithm, you turn the learning rate right, you will get the 1/delta, the 1/gap bound that Schipper was talking this morning. The instant optimal bound. You can get it with the same algorithm. So there you have one algorithm that's optimal for both cases. And again, that's surprising because this kind of FTRL framework is originally proposed only to deal with adversarial case. But turns out that somehow it kind of automatically adapts to the stochastic case as well. Again, Sadori will talk more about this. Yes.
This case is independent of K.
Okay, yes.
So is this the only regularizer for which that invariance is true?
Yes, that's the only one at least I know. Yeah.
Is there some hope of a more general version that whatever the regularizer is shouldn't depend on the number of arms in the minimax case? Like, that should be the right regularizer to choose.
But I mean, okay, learning is something subjective. I can put a k factor here and go k8 at the learning rate. So it makes this more difficult to answer this question. Okay.
For the other corruptible terms, do we need like the alpha parameter of the self-simplicity?
No, that's the beauty. You just set it to be 1/2. Yes. Okay. So okay, I'm not going to talk about how to adapt to stochastic case. So Doris will talk about it. But in the rest of this talk, I will talk about a different kind of adaptive bound, bounds that depend on the specific problem instance in a different way. Okay. So then the motivation is just that the worst case robustness, this kind of root tk, is nice, but it might be overly pessimistic. Okay, your environment might not be really adversarial. Okay, so the question is, can we kind of adapt to easier instances with a smaller regret whenever you are facing with easier instances? Okay, so over the years we have many results along this line, and there are many different ways to measure easiness. Okay, so the first one is kind of the loss of the best arm. Okay, so let me call it L star, which is again the cumulative loss of I star. Okay, so the hope is that whenever this is small, you should suffer smaller regret. So if you have an arm that's actually good, then hopefully the problem is easier to learn. Okay, and that turns out to be indeed the case. You can actually get this kind of regret bound replacing T with L star, just up to some a log factor that's hiding in this O tilde notation. Okay. Again, L star in the worst case T. So in the worst case, you are still getting root TK. But the hope is, again, maybe your best arm is much better than the worst case, which is linear. And in which case, your regret is also much better than root TK. So that's one way to do it. There are several approaches, and I will discuss the second one by Foster et al. Later. Okay, and instead of looking at just the cumulative losses, you can also look at other quantities such as the variance. Okay, so this is just average variance of all the arms. So Li is, I'm using Li to denote the cumulative loss of arm I. Okay, so that this second term is just the mean. So you can get something like this. Again, Q in the worst case T. So in the worst case, you're not getting anything. But hopefully, for many benign environments, Q is much better than T. Okay. And you can also get something even better that depends only on the variance of the best arm, not just the variance of all the arms. Okay, this is you can get root Q star K. And another kind of measures of easiness is the kind of the path length of the losses or the variation over time. Okay, so look at LT minus LT minus 1. Okay, you can look at the max norm over all the arms. You can get this. You can also just look at the variation of only the best arm. Okay, let's go V star, then you can get something like this. So you pay an extra K here, and that turns out to be unavoidable for adaptive adversary, which I'm not going to discuss in detail. And the last one I want to mention is just the kind of the sparsity of rewards. Okay, so I've been using losses, and now I kind of switch to rewards by taking like one vector minus LT, and then count how many non-zero you have. Okay, and so I'm doing this because if you think about it, sparse losses is easy, right? If only a couple few arms have losses, then this is an easy instance. While for sparse rewards, it's a harder problem, right? Only a few arms has reward, and you have to pick those arms. So the sparse rewards is harder, and this is saying that even for the harder case, you can get root TS. So you have no explicit dependence on the number of arms, but only on the sparsity. Okay, so that's also possible. And okay, so these are all nice, and in fact, they also have very nice implication for games. So if you use this algorithm to play games, in particular the first and the third type, you can show that it leads to faster conversions than using the let's say the minimax optimal algorithm. Okay, so I'm not going to discuss this, but the intuition, for example, for this one is just that this is measuring your regret with respect to the variation of the environment. And in a game setting, your environment is kind of determined by your opponents. And your opponents is most likely doing a learning algorithm as well. And most learning algorithms, they are stable. Okay? If your opponents are stable, then it means that your environment is also stable. And that's why you can show that these paths then they are indeed much better than linear T, O of T in those cases. And that's why you can use this bound to get even faster convergence for games. Yes.
So this is a statement about, sorry, this is a statement about all algorithms in this environment, or just algorithms designed with like keeping the path locks in mind, for example.
Wait, your question is like whether every place have to use the same algorithm?
Is it faster convergence in these environments for all algorithms, or algorithms that are designed with these properties in mind?
Yeah, only for this property. That's why I'm trying to tell you why these properties are important. And one reason is that if you have this property, you have faster convergence in games. Yeah, that's what I'm saying here. Yes.
The next one's why V star should help. Could you say a little bit about why L star helps?
Okay. Yes. Frankly, I don't remember. It's from this paper. It's from this poster. Right.
This movement proof goes through.
Oh, so for a price of energy
price of
style,
energy
not for any.
Yeah, right.
Okay, that's.
Okay, so I'm not gonna talk about games. I'm just gonna show you quickly how to achieve the first and the third type of bounds. Okay, again using the FTRL. So the first one, getting root L star. So usually we call it smallest bounds, and you can get it via this algorithm. Okay, again, there are several different approaches. I'm taking one from this Foster et al. Okay. So you do FTRL, but with yet another new regularizer, which is a log barrier. Okay, it looks like this. I mean, in a sense, it's also another limit of Sarah's entropy, but we don't need to worry about that. It's just simply negative log pi. Okay. So let's do this, and again, apply this general bound and see what's the trade-off between the penalty and the stability term now. Okay. So the first thing that's tricky is the penalty. Now you cannot simply bound it by the range, because the range of log barrier is actually infinity. Like when you put all the weight on one arm, then this actually is infinity, right? So that's one kind of subtle thing about log barrier. But it doesn't mean that you cannot use it. In fact, just pick your comparator to be something very close to putting all the weight on I star, but mixed with a uniform, let's say 1/t amount of uniform over all the arms. Okay, so you're almost competing with the best arm, just up to an 1/t term. Okay, so it's easy to say that, to see that it doesn't affect your regret, because this is only 1/t per round. So over T rounds, it only gives you like a 1 regret. Okay, but it helps a lot in terms of bounding the penalty, because now every P star I has the lower bound of 1/tk. So that this log 1/pi thing cannot explode. Okay. And if you do that, you can show that now this penalty term is just bounded by k log t. Okay, so that's one subtle thing about log barrier. Okay, and then now let's look at the stability term again. Let's just do a second derivative, right? First derivative is 1/pi, second derivative is 1/pi squared. So take the inverse, you get p squared. So that's yet even smaller than Sarah's entropy. Okay, and of course, when you take expectation, you get just pt dot lt, which is of order 01. Okay, and now you see that this is a new trade-off. For log barrier, you're getting a k log t penalty versus 01 stability. Okay, so you see that this is actually even worse than Shannon entropy. If you look at the product, you have log t instead of log k. It's not minimax optimal, but the nice thing is that it's this term. Let's not bound it by 01. Let's come back and just bound it. Let's take the optimal eta. And then you get something like this. Your regret is root k expected loss of the algorithm. Okay, and in fact, this actually implies root k loss of the best arm. Okay, there are many ways to do it. One way to see it is that so regret is this term minus L star, right? It's the difference between the loss of your algorithm and L star. So you can see this as the quadratic inequality of root loss of algorithm, then just solve for it, and then you get this. Okay. But the quick message is just that this bound imply the smallest bound that we want. Yes.
Is there any reason to use entropy regularizer instead of log barrier, for example?
Well, for example, it gives you this kind of adaptive bound. Just one advantage.
No, so using entropy regularizer.
Give me the benefit
Does
of
this
using.
regularizer kind of dominate the entropy regularizer?
You mean log barrier?
Yeah.
Whether log barrier dominates? I mean, it depends on what you mean by dominate, but log barrier has many nice properties that I will mention. I mean, this is one of the nice property of log barrier, right?
So what is the negative thing about? Like,
About
why
this?
would I not always use log barrier?
I see. First of all, it gives you the log t term, right? You get log t, entropy is no log t. And second, I mean, when you're dealing with bandit with structure, for example, contextual bandit with adversarial losses, then you have to use entropy somehow, because for all the other regularizer, the penalty term will depend on the number of pores, which I mean polynomially in the number of pores. Only entropy gets you logarithmic dependence. But okay, just for multi-bandits, again, I guess the difference is just log t versus no log t. Is that clear? Okay. So that's how you get this kind of small loss bound. And finally, let me also tell you how to get this path length bound. The bound that depends on the variation of the losses. Okay. So you're gonna still use log barrier as the regularizer in FTRL, but you're gonna do a variation of FTRL. You do something called optimistic or predictive FTRL. Okay. The only difference is just this MT term. Okay. So it's saying that at time t, before I play the game, I will make a prediction MT on the loss vector for this time. Okay, so MT, you should see it as a prediction for LT, and I should construct it based on all the information I have at the beginning of time t. Okay, I will talk about how to construct this later after we see the bounds, but now it's just a general predictor for LT. Okay, let's say you somehow come up with this predictor, and you just put it into this update rule. Okay. And so it turns out that you can prove something like this. With penalty term is still the same, but stability term becomes like how accurate your prediction is, which is very natural, right? This measuring the difference between LT hat and MT with respect to the local norm. Okay. So now let's just do the calculation. Penalty term is the same, nothing changes. It's still just about the log barrier, so it's bounded by k log t. So to really utilize this stability term, what we need to do is use a kind of a variance reduced estimator. Okay, something like this. So okay, when MT is 0, obviously it's just the same as the importance weighted estimator that we had before. And now you do something like that. You subtract MTI in the numerator here, and then plus MTI here. Okay, so again, it's computable and it's unbiased, right? When you take expectation, this cancel with PTI, and minus MTI cancel with plus MTI. So it's still unbiased. The reason we use it is that now if you look at this stability term, okay, which by definition is just this. Okay, now I haven't used the definition of MT yet. Now let's plug in MTI. You see that it's simply this. Okay, so the plus MTI cancel with minus MTI, and then PTI square cancel, and you just get this thing times the indicator. So I can just write it in this way. It's the kind of the error of your predictor for the arm you selected, the square error.
Sorry, did you say how you calculate MT or?
No, I haven't told you. So everything now is for general MT, and in the just a second I will tell you how to pick MT. Okay. So but so far again everything holds as long as you can construct MT at the beginning of time t. Okay. So let me just assume MT is also between 0 and 1, which is then you can just bind by the absolute value. Okay. So. Okay, so if you look at this, if I can pick MT so MT to be LT minus 1, then this is exactly the variation, right? But the thing is just that each time I only see one coordinate. So maybe last round I'm not picking the same arm, so I don't have that information. Okay, And so the natural thing to do is just to instead let MTI to be the most recently observed loss for RMI. Okay, so ideally, I want to use the loss for last round, but I might not have it. So let me just use the most recent recent round that I selected this arm. Okay, and so if you do this, let's just do this simple calculation. The first step is just rewriting. I'm still not using the definition of MT yet. Right, just rewriting sum of I, and then look at all the IT being I. Okay, but now if you look at this term, and by the definition of MT and do a triangle inequality, you just get the variation. Right, this is a simple triangle inequality. Okay, so that's how you get variation out of the stability term. And again, if it means that if the environment is slowly changing, you get your stability term is much better than O of T. Last step, pick the optimal eta, you get this. Any questions? Okay, so at this point we have seen two nice examples of or nice applications of log barrier. So I'm just going to mention a bunch of other nice properties of log barrier without going into detail. So it turns out to be, again, like I said earlier, it's surprisingly powerful for MAB, just for this problem. It might not be useful for, like I said, like contextual bandit and other stuff, but it's just surprisingly powerful for MAB. So earlier, I said that Sarah's entropy enjoyed the best of both worlds. It's optimal both in the adversarial case and the stochastic case. But it turns out that log barrier also enjoys something like this. So it's even discovered even earlier than the Sarah's entropy. Okay, and it's also a tool to stabilize the algorithm. So if you look at the trade-off, the penalty and stability trade-off, log barrier has the smallest stability. So it means that this is the most stable algorithm in this spectrum. Okay, so you can use it as a tool to stabilize the algorithm and to get some very nice properties, especially when combined with other regularizers. And again, I'm not going to talk about details, but we have been using. There's a sequence of papers combining log barrier with all kind of different other regularizers to achieve all kind of different nice properties. And finally, there's also a trick that you can do for a log barrier. If you increase eta occasionally in some specific way that, again, I'm not going to talk about, then you will obtain a negative regret term in your regress for free. Okay, you will get everything you have before, and then a negative term. Okay, that looks like this. So the negative term depends on the probability of picking the best arm. So if at some point in this learning process, you pick the best arm with a very small probability, so that actually means that even though I star is overly the best, maybe at some point it wasn't the best, and your algorithm was picking something even better. So that's why it's possible to obtain something negative. So you're doing even better than I star at some point. Okay. And this kind of negative term is very useful, turns out. You can use it to do many different things. But we first realized it in this 2017 paper when we are trying to combine different bandit algorithms, which is a notoriously difficult problem. I guess I will skip this. But another very easy to see application is obtaining high probability bound. So far I have been discussing expected bound. So when you try to derive a high probability bound, you need to do a concentration. Okay. So for the concentration around the optimal arm, the variance is exactly something like this. So let's say when you apply like Freeman, you get a variance that looks like this. And then this negative term will exactly cancel the variance. And that's how you can get a high probability bound for bandit. That's one way to do it for MAB, but as far as I know, it's the only efficient and optimal way to do it for something called linear bandits. Okay, so that's just a slide to convince you that log barrier turns out to be very useful for this problem. So, so there's some open questions. Should I Should I stop at 15 or? Okay, then maybe let me skip. Okay, so let me talk about only the second one. Okay, so the first one is just about log terms. Can I get this without log terms? So the one I show you has log t. So how can I remove it? Kind of a niche problem. The second one is probably more interesting. So can I get second order pass-reference bound? So by that, I mean the following. So all the bounds I have shown you, something like this, is first order in the sense that there's no square here. Okay. So second order pass-reference bound would be something like this. And I'm asking whether this is obtainable, which is unknown. Okay. The answer is yes for full information. That's well known. And another reason that you should care about it is that, again, going back to this GAM application, first order means 1/t to a 3/4 convergence, and second order means even faster 1/t. And that's why we want to get this. Right? It's meaningful to get this. And I'm saying that even for two arms and the case, let's assume the environment is super stable where the variation is just 0.1, we don't have an answer for this question. Okay, so I invite many of you who are interested to work on this. All right, so let me conclude. So let me conclude by first telling you again, highlighting the differences between full information case and the bandit case. So we have seen there's of course a difference in the minimax regret. So if it's full information, you get root T log K. But in bandit, when you have only roughly 1/k fraction of the information, you should pay for K, root K here. Okay. And for adaptive regret, we discussed all these bounds. So in full information, you can get all these even with second order pass lengths. Okay. So these are the things that we have discussed today. And I will roughly go over something that that we didn't discuss, but it is kind of interesting differences between these two cases. So the first one is something called switching cost. So sometimes you have application where you don't want to frequently switch between different arms. So let's say you're doing dynamic pricing, each arm is a price. Obviously, you don't want to change your price every day. Okay? So one way to kind of formulate this problem is to, let's say your goal is to minimize regret plus the number of switchings over the T rounds. Okay, so that's what I mean by switching cost. And it turns out that in full information case, you can get it for free. So you can still get the minimax optimal bound, and with only root T switches. So you can get the exact same thing. But turns out that for Bandit, you really have to pay for something. The best thing you can do is indeed a T to a 2/3. So if you insist on root T regret, then you have to switch for linear time.
So the algorithm isn't penalized. I mean, the opt isn't penalized for switching. Oh, you're comparing to the best fixed arm, so there is no switches.
Yes, I'm still competing with the best fixed arm, but I penalize myself if I switch. Okay. Again, you cannot get root T regret and sublinear switches. The best trade-off you can get is root T regret and T to a 2/3 regret and T to a 2/3 number of switches. Another, this thing is the interval regret that I hinted earlier. So standard regret compete with best arm over all time. So now let's look at interval regret which compete with the best arm on some interval. Okay. For any interval from S to T, let's look at the regret only for that interval. Okay, which is useful for a dynamic environment where you don't have a fixed arm that's good overall. Okay. So, and of course, you want to do it, you want to have a good regret simultaneously for all intervals. Okay. In full information case, you get the most natural bound, root T minus S log K. Okay, so the length of the interval log K, that's the best you can get. Okay. For Bandit, turns out that provably you cannot get this, and you can get something like root TK. Even though the interval is small, you still need to pay for T instead of the length of the interval. Okay. And finally, the last thing is very related to interval regret. It's something called switching regret, not to be confused with switching cost. So it's saying that let's compete with a sequence of changing arms, just switches at most S times. Switches at most S times. So again, this is used for like dynamic environment where you don't have a fixed good arm. So let's say if I allow it to switch S times, maybe I can find a good sequence. Okay. So in this case, again, for unknown S, you can get root ST log K in the full info case. And that's simply an implication of interval regret because you just sum up the regret on every interval and apply a Cauchy square. That's why the S is appearing inside the square root. Okay. So for the Bandit case, it's actually quite intriguing. For adaptive adversary, just a recent paper by Marinov and Zimmer show that it's impossible. For our previous adversary, we don't know. That's also open. And of course, by summing up this bound, you can trivially get S root TK. So that's kind of trivially what you can achieve. And this is ideally what you want to achieve, but we don't know yet how to do it for our previous adversary or whether it's possible. All right, I'm happy to discuss all these after my talk. Let me just summarize the technique. Central technique, as you can see already, is to design an algorithm for the full info case first. So I discussed FTRL in this talk, but there are at least two other general framework. One is online mirror design, one is for the perturbed leader. You can also use this framework for Bandit as well. The second is design loss estimators, and as you probably know now, the real challenge is that you need to find the right combination of these two that so that the variance is well controlled using the local norm in the stability term. And this technique is applicable for many other problems, such as Bandit with all sorts of structures, similar to what Shipper was saying this morning. You can also do it for a more general problem called partial monitoring that captures things like Apple tasting, dynamic pricing, etc. And of course, you can also do it for reinforcement learning as well. You can generalize some of these techniques for learning Markov decision processes, even with adversarial losses. And with that, I will just stop here. Thanks for your attention.
We have time for some questions. So just a brief announcement before that. So after this, we'll have a tea. But instead of having it inside, the staff have put the tea next to the door, and the suggestion would be you can grab the tea and snacks and then head outside so that you don't have to wear masks. But yeah, I'll throw it open to questions first.
I'm curious about, you mentioned that logberry is good for stability, having small stability or good stability. Is that true for general measures of stability, like stability against observation error, things like that, or is just the term that we call stability term to be small?
In a sense, yes. So I mentioned this at best of those whole thing, that it also adapts to stochastic losses. So in fact, it's also so it's near optimal for stochastic losses, but it also adapts to the corruption to the stochastic losses. So that's kind of related to this. If you have error in your observation, you can also adapt to it. So in that sense, it is stable even against those.
This paper discussed those kind of stuff. Do you know?
My original paper doesn't, but this one does. And I am sure Doris will mention a lot in the next talk.
Thanks.
One question about, so Shikha is about the losses versus gains. It seems that one natural way of doing reward would be if you had an upper bound and the reward, just to reward minus.
Yes.
Think of loss as reward minus estimate.
That's exactly yes.
Is that known to be optimal in all cases? Like, do we know any case where we need to do something fancier? Or?
Not that I'm aware of. Yeah, you just need to do that. Yeah.
So just this is enough for loss and
yes.
I have a question about the regret that there are sleeping costs. Like, is there a matching lower bound saying that the order has to be the number of floors?
Yes, I'm going to say that yes. So yes, that's the best thing.
Oh, okay.
So there's a lower bound. I mean, this paper. I mean, the upper bound is actually trivial. You do just epoching. I can tell you more. But this paper is mostly just about lower bound.
Oh.
And it's very interesting because we don't really have a lot of T2 lower bound in this kind of methodology. Yes.
You mentioned there's like an asymmetry here, when you have like forwards versus.
Yes.
Why is that exactly?
Okay, I mean, it's not a real symmetric because, like I said, you just need to translate it to losses, and I'm just saying that okay, it's probably 2 slides ago, but I'm saying that for some algorithm, you cannot do negative losses as the rewards because that will discourage exploration for that specific algorithm.
I see, for the specific algorithm.
Yes.
But if you do that shifting, do you have to do it before you compute L hat? Because L hat will not.
Yes, you will need to do it.
Before you
Yes.
Yeah, I mean, it seemed like this was giving EXP4 if you just naturally think of 1 minus your estimator. You just got EXP4. So.
I guess if you care about bounds that scale with the gain of the best
then
target,
it will suffer.
then this will break that.
Yeah.
That's what
Then
I
1 minus loss will not.
You get a worst case.
Yeah, that was kind of what I was thinking. Yeah, it's
Or
not-
variance that depend on variance.
This may be a good question for T. So
Yeah.
let's declare that. So 345, everyone. So Doris will tell us why it doesn't work. Why it does work. Another interesting thing. See you later.